So in this video, we're going to shift gears from focusing on derivatives to focusing on antiderivatives. So there's a sense in which the antiderivative is the inverse operation of taking a derivative. And so here's the basic idea. We're going to start with the function little f of x. And when we're finding an antiderivative, we're looking for a function big F of x for which the derivative of big F of x is little f of x. So here's an example. It says find an antiderivative, and we didn't use the word the here on purpose. So I'm using the indefinite article an on purpose. So it says find an antiderivative for f of x equals x squared. So to find an antiderivative, we're looking to find a function big F of x whose derivative is x squared. And so there's some guesswork that goes into this. You're really looking at the function x squared and you're saying, whose derivative am I? And you're looking to find that function whose derivative is x squared. So I see that I've got an x squared, so I can think of this maybe in terms of the power rule, that perhaps if I make a guess, I'm going to guess that the antiderivative of x squared is x cubed. And this would be a good guess, because if we were to calculate f prime, we know we would bring the exponent 3 down front, but then we would also reduce that exponent by 1, and that would give us an x squared term, which is what we have here. But then what we want to notice is that taking the derivative of x cubed would give us 3x squared, and that's not what I have here. And the way that you check your work, if you find an antiderivative, you take the derivative of the antiderivative and see if you get back the original function. So in this case, I'd say, hey, I guessed it's x cubed, because when I take the derivative of x cubed, I get a 2 in the exponent position on x, which is what I have here. But oh, I got this 3 in front of the x squared. And so then the question you just need to ask yourself is, how can I tweak my guess so that I get what I want, namely a 1x squared? Well, you can say, well, I'm going to put a 1/3 in front, because then when I take the derivative, what am I going to get? The derivative of big F of x equals 1/3 x cubed is going to be 1/3 times the constant times the 3 would come down from the exponent position, and we would reduce that exponent by 1, so we get 3 minus 1 is 2, and 1/3 of 3 is 1x squared, and voila, we have it. And antiderivative of x squared is 1/3 x cubed, because the derivative of 1/3 x cubed is x squared. We want to notice, though, is that this answer isn't unique. So, for example, I could make another guess. I could say, I'm going to make a guess for the antiderivative of x squared. I'm going to guess that the antiderivative is 1/3 x cubed, but I'm going to go plus 5. And then we could check our work and say, hey, is this an antiderivative of x squared? Well, to check your work, you take the derivative of your guess, and you see if you get the x squared back. So in this case, the derivative would be 1/3 times 3x squared plus the derivative of 5 is 0. So I wind up still getting just x squared. So this is also an antiderivative of x squared. So for example, we could say what's an antiderivative for f of x equals the sine of x. So again, we would be looking for a function big F of x whose derivative is sine x. So a good guess would be cosine of x. But then if we tested that guess, we would get f prime of x. We would need to take the derivative of this, and the derivative of cosine is minus the sine of x. And that isn't quite what I have here. What I have here is the sine of x. So my guess, cosine of x, didn't quite give me what I needed. It gave me a negative sign here. So I can ask myself, how can I adjust my guess so that I get the sine of x? So we'll try the opposite of the cosine of x. We'll put a negative sign in front, trying to kill the negative that we get when we differentiate the cosine function. So if we take the derivative now, we'd get the opposite of the derivative of cosine is minus the sine. And now the double negation will cancel and give us the sine of x. Now, just like before, what we want to notice is that this antiderivative isn't unique. So for example, I could make a second guess for an antiderivative. I could say I'm going to guess the opposite of cosine of x minus 2. And then I could check my work by taking the derivative. F prime of my second guess is equal to the opposite of the derivative of cosine is minus the sine, minus the derivative of 2 is 0. The double negation simplifies to the positive sine x. Minus 0 is just sine x. So I've checked my work. This is also an antiderivative of the sine of x. And so what you want to notice is that adding a constant to your guess isn't going to change the derivative. So for example, we could say what's the antiderivative of f of x equals 6x? Well, we would be looking for a function big F of x whose derivative f prime of x is equal to 6x. And so a good guess, this has a 1 in the exponent position, a good guess would be x squared. But if we took the derivative of x squared, we would get 2x, which isn't a 6. So you say, how could I change this to get a 6? Well, I'd need to multiply it by 3. 3 times 2 would give me my 6. So I'm going to add a 3 in front of the x squared here, so that when I take the derivative of 3x squared, I get 3 times 2 times x to the first is 6x. But what I want to notice is that if I have a 3x squared, which is an antiderivative of 6x, because its derivative is 6x, if I have a 3x squared, adding any constant to it isn't going to change the derivative. If I make a guess for an antiderivative of 3x squared plus 2, when I take the derivative g prime of x, I'm going to get 6x plus the derivative of 2 is 0. I get 6x. So this function is an antiderivative of 6x. If I make my guess 3x squared minus 100, this will also be an antiderivative because h prime of x will equal 6x minus 0 equals 6x. The derivative of a constant is 0. R of x, I could make my guess 3x squared plus the square root of 2, and this will also be an antiderivative of 6x because the derivative of 3x squared plus the square root of x is 6x plus the derivative of the square root of 2, which is a constant, is just 0. So what I want to recognize is that I can add any constant I want to this base antiderivative. So if q of x is equal to 3x squared, I can add any arbitrary constant I want, and the result will be that the derivative will give me 6x. So the derivative q prime would be 6x plus the derivative of a constant is 0 equals 6x. So in general, to find the antiderivative, we're really looking for the family of functions that is the antiderivative of the function we're starting with, and that function family we get by simply adding a constant to the base function whose derivative is 6x and saying, hey, you can add any constant you want and the derivative will still turn out to be 6x. And this constant that we add on is called the constant of integration. And the process of finding an antiderivative, we call that process integration. So one slide to kind of formalize those concepts from that previous slide. This says, hey, if you can find big F of x and big G of x, and both of them are antiderivatives of a function little f of x, then g of x only differs from big F of x by some constant. So for example, if I want to find an antiderivative for 3x squared minus 4x, what I want to notice is that there are infinitely many functions. I have graphed a few of them here whose derivatives, there are infinitely many functions whose derivatives are 3x squared minus 4x. So you can see for each of these third degree polynomials here, the variable part matches. The variable part matches all the way down, and the derivative of the variable part is going to be 3x squared minus 4x. this guy right here, and they differ from each other only by constants. So if I take the derivative of any of these, I'm going to get 3x squared minus 4x, because the derivative of the constant terms will be 0. So the antiderivative for d of x equals 3x squared minus 4x right here is going to be x cubed minus 2x squared plus a constant of integration. There are infinitely many functions whose derivatives are 3x squared minus 4x, and they differ from each other only by a constant. The other way to think about this is to think back to pre-calculus. When you have a base function and you add a constant to a function, all you're doing is a vertical translation of that function, either up the y-axis or down the y-axis, and vertically translating a function won't change the slopes of the tangent lines of the function. So again, finding an antiderivative is simply a matter of finding a base function, whose derivative is the function that you start with, and then adding on a constant of integration. So in the next video, what we're going to do is come up with notation for antidifferentiation, for finding antiderivatives or integrating. We're going to come up with or establish the notation for it, and then we're going to review all of the differentiation rules that we've learned up to this video, because those are the rules that we're going to use to work backwards to find antiderivatives.